Now we shall see the classical problems of synchronization. There are three classical problems of synchronization. One is bounded buffer problem. Second one is reader-writer's problem. Third one is dining philosopher's problem. Dining philosopher's problem. First one is bounded buffer problem. Bounded buffer problem. Assume that there are n number of buffers. Assume that there is a pool which contains n number of buffers, and each buffer can hold one item in it. Each buffer can hold one item in it. And next, since we are dealing with semaphore solution, semaphore mutex, semaphore full and semaphore empty are three semaphores which we are making use of it in order to produce the solution, in order to give the solution. So the semaphore mutex provides mutual exclusion. This particular semaphore mutex provides mutual exclusion, and it is initialized to value 1. It is initialized to value 1. Next, other two semaphores, that is semaphore full and semaphore empty. Semaphore full and semaphore empty are used to count the number of empty and full buffers. To count the number of empty buffers and full buffers. And semaphore full is initialized to 0 and semaphore empty is initialized to value n. Value n, that is n number of n buffers in the given problem. Now, as you can recall your producer-consumer problem, producer is a one who produces the items, and this is how the code looks like, and consumer is a one who is going to consume the items. So with respect to your mutex, full mutex, semaphore mutex and semaphore full, we are going to write the structure of your consumer and structure of your producer as shown in this slide. Next, second problem is reader-writer's problem. What is this reader-writer's problem? A data set is shared among a number of concurrent processes. It tells that there are two conditions. First one is reader's condition, that is only read the data set. The readers can only read the data set. They cannot perform any updates. And writers, they can do both read as well as write. But what is the problem? The problem is that it allows multiple readers to read at the same time. The problem is it allows multiple readers to read at the same time, and only one single writer can access the shared data at the same time. Only one single writer can access the shared data at the same time. I repeat the problem. It tells that there is a shared resource which is accessed by multiple processes. What is this multiple processes? With an example, we'll see here. As you can see here, there is a text document. Which is a shared resource. Two processes are there, reader as well as writer. It tells that any number of readers can access the shared resource. That is n number of readers can access the shared resource. Writer, only single writer can access the shared resource. That is, when a writer is trying to write data into the shared resource, no other process can access the resource. First condition. Second is, a writer cannot write to the resource if there are non-zero number of readers accessing the resource. If nobody is accessing the resource, what is the use of writer writing the data? And if writer is trying to write some data into the resource, no other readers or processors should access the resource. But note that at the time of writing, no reading is allowed, and at the time of reading, no writing is allowed. No writing is allowed. So this is the problem statement. So for this problem statement, we can provide solution using semaphore technique. Semaphore technique. What is this semaphore technique? How does it help us? Semaphore techniques, it provides two semaphores. One is mutex, one more is wait. What does your mutex do? Mutex is a variable which keeps track of the number of readers count. And here initially both the variables that is or semaphores is initialized to 1. Semaphore mutex is equal to 1, semaphore wait equal to 1. Then how does my writer process look like? It tells that only a single writer, I repeat, only a single writer can access the shared resource. So I can tell that wait of W, writing is performed. After writing is performed, signal it, telling that writing is over. That is, increment the value of W so that other writer or reader can access the shared data. Other reader or writer can access the shared resource or shared file or shared data. This is how your writer process looks, since there is only one writer accessing the file at the same time. But how does your reader process look now? It tells that the reader, any number of readers can access the shared resource. Any number of readers can access the shared resource. That is, I keep track of the readers. I need to keep track of the readers. For that, I'll make use of read count variable. Read underscore count variable. What does this read underscore variable do? This read underscore variable or read underscore count variable will count the number of readers accessing the resources. And in order to keep track of this read underscore count variable, I will make use of my mutex semaphore. In order to access read underscore count variable, we will make use of mutex. With the help of this mutex, only one reader can access the resource. With the help of the mutex, we can see to that only one reader is going to access the resource. So first, wait of mutex, increment the count value, read plus plus, after acquiring the lock to that particular process. Next, check if it is the first reader. Check if it is first reader. That is, if read underscore count equal to 1, then confirm that it is a first reader, give the lock to first reader. After that, if in case after the writing of the first reader is completed, he can release the lock. Else, if the second reader comes, then also the first reader should release the lock. He can release the lock by signaling. That is, signal of mutex, and release the lock and give the lock to the second reader. And this process keeps on repeating until n number of readers try to access the document or shared resource. So when n number of readers are trying to access the same resource, then you can tell wait of mutex read underscore count minus. That is, now it is confirmed that since n number of readers are there, the document will never be free. The document will never be released. It is never free. That is why we tell here, or we decrement the count variable, read underscore count minus, and check now whether it is the last reader who is reading the document or reading the shared resource. That is, if read underscore count equal to 0, signal of W, check that whether it is the last reader. If it is the last reader, complete the reading procedure and release the lock. That is, signal of mutex, and now you can tell that the shared resource is or can be accessed by any of the writers who are willing to access that particular data. This is how, or this is your structure of a read process. Next problem, or the last problem, is dining philosopher's problem. Dining philosopher's problem. In this problem, it tells that there are 5 philosophers sitting around a circular table. Dining table has 5 chopsticks and bowl of rice in the middle. Philosophers can do either of the two things. One is they can either eat or they can think. When a philosopher wants to eat, he uses 2 chopsticks. He uses 2 chopsticks. When a philosopher wants to think, he keeps down both the chopsticks. So the problem is that no philosopher will starve. The problem is that no philosopher will starve. No philosopher will starve. But we should see to that the philosophers will either eat or think. So how to give the solution? We can provide solution using semaphore technique. That is, philosopher must be allowed to pick up chopsticks if both left and right side chopsticks are available. Or another solution is that allow only 4 philosophers to sit in the circular table. Sit in the circular table. Now, how does this look like? Your structure, the structure of philosopher, how does it look like? For structure of philosopher, I. Weight of chopstick of I. Weight of chopstick of I. Then weight of chopstick of I plus 1. That is the next chopstick. Here I tell that I is nothing but the first chopstick. Next, increment the value of chopstick. Mod 5. Mod 5. Why? Because I know that it is a circular table. Circular table wherein the number is going to repeat. The number is going to repeat. 1, 2, 3, 4, 5. After the 5th philosopher, after the 5th philosopher has completed eating or thinking, again philosopher 1 should get his chance, since it is a circular table. If you see here, 1, 2, 3, 4, 5, again 1 is going to repeat. The first philosopher will repeat. That is why it is mod 5. That is, if I tell it as just I plus, if I tell it as just I plus 1, then my count value will be 6, which is not a valid one. So since it is mod 5, even though the counter value will be 5, that is your I value is 5, 5 plus 1 equal to 6, then 6 mod 5, sorry, 6 mod 5 will be equal to 1. That is, again your first philosopher will get his turn. Your first philosopher will get his turn. So after this, that is why we have written the condition as I plus 1 mod 5. Then after these two conditions are satisfied, then ask the philosopher to eat. After this is over, release the chopsticks. Release the chopsticks. That is, release the chopsticks. Then ask them to think. Ask them to think. This is your basic structure of philosopher problem. Now, here, even though I provide solution, there is one more problem arising. That problem is nothing but deadlock. Deadlock. So, what is this deadlock? We'll see what is the deadlock. That is, a process is holding the resource and the resource is not being released, but the same resource is being requested by other process also. That is the meaning of deadlock. What is this deadlock? In detail we will study in next module. As of now, for providing solution, we can tell that allow at most 4 philosophers, as I have told in the beginning. Then allow a philosopher to pick up forks only if both are available. That is, left hand side and right hand side are available. picking must be done in a critical section, that is only one process at a time, one philosopher at a time. Next, use an asymmetric solution, that is number the philosophers. Ordered number philosophers picks first the left chopstick and then the right chopstick. Even numbered philosopher picks up first the right chopstick and then the left chopsticks. These are the ways of handling your deadlock condition. Next, one more thing is, with the help of semaphore, we can provide the solution for dining philosopher. One more solution can also be given by something called as monitors. What is this monitors? As you can see here, suppose that a process interchanges the order in which wait and signal operation on the semaphore mutex are executed, resulting in the following solution, that is your signal mutex critical section and then your wait mutex, which is your old procedure, old way of executing the process. So here there can be an error. In these situations, the programming error can occur or an uncooperative programming can occur here. So next, if you see that here I am telling that signal of mutex, critical section, wait of mutex. When I tell this, in the critical section there are chances of n number of processes running at the same time or executing in the critical section. So next is that, suppose that a process replaces signal mutex with wait mutex. Then what happens? Deadlock might occur. Or if the process omits the wait mutex or signal mutex or both, then in this case either mutual exclusion is violated or deadlock can occur. So all these are nothing but the errors. And in order to deal with such type of errors, researchers have developed a high-level language construct called as monitors, which is a high-level language construct. Then what is this monitor? A monitor is nothing but an abstract data type. It is an abstract data type which encapsulates private data with public methods to operate on that particular data. That is an abstract data type wherein the internal variables will only access the code within the procedures. And also see to that only one process may be active with the monitor at a time. How do I declare, or what is the syntax for writing this monitor? I tell monitor name, then write the variables which I want to declare, then followed with variables I am going to write the procedures. Procedure 1, 2, 3 up to n procedures, and then initialize my code. Call the code. This is how your syntax of monitor looks like. Next, however, the monitor construct is defined so far and it is not sufficiently powerful for modeling some synchronization schemes. For this purpose, we need to define additional synchronization mechanisms, and these mechanisms can be provided with the help of condition variables, that is condition x, y variables. Condition x, y variables. That is, two operations are allowed on condition variable. The first one is x wait and the second one is x signal, x dot signal and x dot wait. These are the two operations which are provided with the help of two variables, and it is as shown here, as shown in figure, wherein this is the schematic view of a monitor, wherein you have only your shared variables and your n number of procedures, whereas with the condition variables, that is x dot wait and x dot signal. Your x dot wait means that the process invoking the operation is suspended until another process invokes. I repeat, the process that invokes the operation will be suspended until another process invokes. Then signal x dot signal operation will resume exactly one suspended process. Whichever process is suspended, that process will be resumed, and if no process is suspended, then signal operation has no effect. It has no effect, that is the state of x is the same as if the operation had never been executed, and it is as shown in this diagram, wherein you have these two variables x and y, q's associated with xy variable conditions inside your shared area. Now suppose that when the x dot signal operation invokes by a process P, there exists a suspended process Q associated with condition x. And clearly, if the suspended process Q is allowed to resume the execution, then the signaling process P must wait. Otherwise, both process P and Q would be active simultaneously within the monitor. Under such situations, two things can happen. One is signal and wait, another one is signal and continue. Signal and wait and signal and continue. Signal and wait, it tells that process P to wait until Q leaves the monitor or waits for another condition, and signal and continue tells that process Q to wait until P leaves the monitor or waits for another condition. And this is how the solution with respect to the dining philosopher problem using monitors, which is a high level language. Here we are going to declare a data structure called enum, which has variables thinking, hungry and eating, and state is 5. Why? Because you are aware that there are 5 philosophers and it is a circular queue. Now how does it work? First, each philosopher I invokes the operation pickup. Each philosopher I invokes the operation pickup, and that is operation pickup in order to select your chopstick. After eating, put down the chopstick in the sequence. Put down the chopstick. That is when he is going to think, and it works in the following sequence. That is, first is dining philosopher dot pickup of I. After he picks up, he is going to eat. Then dining philosopher dot put down is going to put down the chopstick, and then is going to think. And this is the best solution using your monitors. That is dining philosopher problem with respect to monitors solution. But here deadlock will not arise, but still there is starvation. Starvation is possible in this particular case. Thank you.